This video clip is designed to accompany subsection 1.2 in the lecture notes, the topic of divisibility, greatest common divisors, and so forth. I shan't cover exactly the same ground in these videos as in the notes. I recommend you look at the video first and then read the corresponding section on the lecture notes. The examples won't necessarily be identical, and I may present things in a different way. But the underlying maths essentially will be the same. So I want to remind you about divisibility of integers. So here we'll, for the most part, be talking about integers. I denote the set of integers by z, written like that. So we're talking about positive or negative whole numbers, including 0. And let's suppose that a and b are integers. What I want to do is consider the possibility that b divides a. So what does this actually mean? So then, I won't make this a formal definition, but the phrase b divides a simply means that there exists another integer, say q, which is an integer, as I said, and q is the quotient, so that means we're saying that b is equal, a is equal to q times b. That's what we mean when we say b divides a, and in symbols we write this b vertical line a. b divides a is written like that. So you can now check with examples. So let me give you some examples. So I just took a number at random actually. So there's a well-known test for divisibility by 3, for example. So let's start with that. 3 obviously divides itself. It does not divide 34, nor does it divide 343, because the digits here do not add up to a multiple of 3. However, what do they add up to? They add up to 10. So if I add a 5 here, the sum of these 4 digits is 15. So that is a multiple of 3, so one knows that this number 3,435 is divisible by 3. So 3 does divide this. Let's actually check that. So we could say this is true because 3,435 is equal to, let's actually do the division by 3. So it's equal to 3 times. I sometimes write times with an asterisk as if I was computing when I'm using actual numbers to avoid any ambiguity. So this is 3 times something. What is the something? Well, I can divide longhand, so it's 1, 1, 4, 5. 1,145. So we know now, I mean, another example is that 5, well, there's a test, there's a more obvious test for divisibility by 5. If the last digit is 5 or 0, we know the number is divisible by 5. So we may as well divide 1145. That will be exactly divisible by 5. So this is also true, and we can actually do the division. 5 into 11 goes twice, 1 left over, twice again, 4 left over, 5 9s are 45. So the quotient in this case, q, is 229. Now, unfortunately, I have to stop there because this is a prime number. 229 is a prime number. How do I check it's a prime number? So prime means that it's only divisible by 1 in itself. I need to check that there are no other numbers that divide 229. Well, remember how to do this. 229, it's almost the same as 15 squared. 15 squared is 225. So we know that if there were a prime factor of this number other than itself, that number couldn't be bigger than 15. 15 is not a prime, so it couldn't be bigger than 13. So we only have to check actually primes up to and including 13. Well, there are tests for divisibility by all of those except 7 and 13. So we really just have to check that this is not divisible by 7 and it's not divisible by 13, and you can do that immediately. So this is essentially prime because we just have to test divisibility by 7 and 13, and that fails. So this must be a prime number. So, well, perhaps at this point I should remind you that a prime number, just to remind you that the smallest prime is regarded as 2. So let's say remind you that recall that let me just say it like this: a positive integer p at least 2 is called prime. If it is only divisible, well, how can I say this? If, let's write it in symbols. If m is a positive integer and if m divides p, then that implies there are only two possibilities, namely that m is equal to 1 or m is equal to p. Now, just to emphasize, 1 is not regarded as a prime number. Historically, some people did regard it as a prime number, but it's rather special because in terms of algebra, it's called a unit. And we don't normally regard 1 as a prime number. So 2 is the only even prime number, all the other prime numbers are odd. We'll only deal with positive integers. One could conceivably think of -2 as a prime number. Algebraically that makes sense, but we won't need to do that. Okay, let me give you 1 or 2 other examples of divisibility. Because it's important to recall the definition I gave you to understand, for example, that any number divides 0. So note that any number divides 0. For example, 7. So why does 7 divide 0? This is because, remember what the definition is. We have to find a quotient. We have to be able to write the number a, which here is 0, as an integer times the number b. Well, we can do that because, of course, 0 is equal to 7 times 0. I put q on the left before, it doesn't matter, but anyway. So any number divides 0, but, of course, 0 does not divide a non-zero number because I can't write, because, if you like, there does not exist q, an integer, such that 7 is equal to q times 0. So just remember that any number does divide 0. Okay, let's go on, and let me remind you what the definition of the greatest common divisor is. So let A and B be integers again. Then the greatest common divisor of A and B, and this is sometimes also denoted or called the highest common factor of A and B. You might occasionally see that. It is, as the word suggests, it is the greatest. Let's use this terminology. It is the greatest positive integer. We'll always use positive integer, whole number, that divides both A and B. That divides is a factor of, means that divides A and B. So again, a simple example. What is the greatest common divisor of 168? It's a favourite number of mine because it has lots of prime factors, and 60. Well, one way of understanding the greatest common divisor is to remember that any integer can be factored into a product of prime numbers, and the greatest common divisor will essentially take the factors in common. So if we, for small numbers, unfortunately this technique won't work if the numbers are big, but for small numbers we can actually do the prime factorizations. So 168 is divisible by 7. It's 7 times 24, 24, which is the same thing as 2 to the 3 times 3, 3/8 24 times 7. Whereas 60, of course, is 5 times 12. 12 is 2 squared times 3 times 5. So if you look at those prime factors, you see if you want to take the biggest number which has factors in common, you're going to have a 2 squared, you're going to have a 3, but nothing else. So that's equal to 12. So of course the greatest common divisor is 12. Now, the problem is that when we have big numbers, of course, we can't use that technique, and there is Euclid's algorithm, which we'll be talking about in the future. You've probably seen that before, which very quickly computes the greatest common divisor of two integers. But let me give you a proposition concerning the greatest common divisor, and let me say it like this. I'm going to say it slightly differently to the way it's phrased in the notes. And here, if everything up to this point has been familiar, we're now getting into the sort of more algebraic territory, maybe a little less familiar. So let me write this as a proposition. And let me denote by n. Again, I've got integers a and b still. Let n be their shorthand for their greatest common divisor. I could have called it g, but n is more common notation for an integer. Then the proposition tells me that if I take the set consisting of, if you like, I can use the linear algebra terminology, linear combinations of a and b, but I just mean with integers. So x times a plus y times b, and here a and b are fixed, but x and y can be any integers. So x and y range vary over the set of integers, so that's an infinite set. This set is the same as the set of all multiples of n. So it's the same as x times n, where again x ranges over all integers. Now, if you know your algebra, ring theory, these sets are both examples of what are called ideals. And we're really saying that this ideal is what's called principal because it consists of all the multiples of a given element n. But you don't need to know that, provided you understand the statement I'm making here. Again, I want to give you an example because this is a very important result. It has various consequences. And the example, move my coffee cup out of the way. The example is this, so I'm just again choosing numbers more or less at random. Take the greatest common divisor of 7 and 31. Well, 31 is a prime number, so the greatest common divisor of 7 and 31 has to be 1 because 7 does not divide 31. This is a prime number. You should really know by heart all the primes up to 100, say, I think. Anyway, so the question is, this greatest common divisor, n is in this set. This set here contains n. Let's write it like this. This set here contains the element n. So therefore, n is also in this set. Actually, maybe I should add another sentence. So let me squeeze in a sentence here. So a corollary of this proposition, let me say it like this, is that so the greatest common divisor of A and B, which is n, is in this set. It's in this set. In fact, it's the smallest element of this set. So it's the smallest positive, this symbol means positive integer of the form xa plus yb. So the greatest common divisor can be written in the form xa plus yb, and it's actually the smallest positive integer that can be so written. Okay, so I should have said that before doing my example. So in this case, 7 and 31, they're called co-prime because their greatest common divisor is 1. So we know it must be possible to write this number 1 as 7 times, well, x if you like, times 7, or 7x, plus y times 31. So 31y. The question is, what are the integers x and y? What are they? And here you can just spot them, you see, because 31 is the biggest number. So let's just take multiples of 31, and we don't have to look very far. Twice 31 is 62, and yet 9 sevens are 63. Those are the sort of 12 times 12 tables that I learnt. That was always the hardest. 7 nines are 63. But anyway, that means that we know what x and y, well, we know one solution here. Of course, there will be infinitely many solutions, but we can take x to be 9, so 7 times 9, and we can take y to be minus 2. So I'll say it like that, 31 times minus 2. That's a simple example. But we'll see that you can extend Euclid's algorithm to actually find mechanically the integer solutions x and y of this equation. Now, this proposition has some important corollaries. Let me just say, I'm not going to prove the proposition here, it's proved in the notes, but the proof of the proposition, uses what's sometimes called the division algorithm. Let me just call it a fact. Uses the fact that given integers a and b, there exists, so we're not necessarily in the situation where B divides A, but we can always get a remainder. So there exists in the general situation not just a Q, but also an R, integers Q and R, such that if we try and divide A by B, we'll get our quotient, but we may need a remainder term R, but we can always choose the remainder term. It could of course be 0, but we can always choose it to be strictly less than B. So that's the so-called division algorithm, sometimes called, and there's a sort of formula for Q in the sense that so in fact the reason is sort of obvious in the sense is that Q is simply, you can simply define Q as the biggest integer which is less than or equal to A over B. So that's sometimes called the floor, if you're doing computing, of A over B, and sometimes written like this. Okay, so this is the greatest integer. Less than or equal to, I'll say this in symbols, you shouldn't really mix symbols with words, but less than or equal to A over B. Anyway, the proof of the proposition uses that fact, and you can write down the proof yourself or try and understand it from the lecture notes. I won't say more about that, but I want to mention two corollaries which are given in the notes. So corollary 1 of the proposition is that, almost obvious, if we have M that divides A and M that divides B, so M is a common factor of A and B, in that case, of course, it might not be the greatest common factor, so we know it's less than or equal to the greatest common divisor, but we can actually say it divides the greatest common divisor. Okay, that's a corollary. And why is that? Well, the greatest common divisor, we know, has the form XA plus YB. So now the corollary is obvious, because if M divides A and M divides B, then M has to divide this object here, because there will be some X and Y for which this is true. So this is true for some X and Y. So that makes this corollary obvious. So a common factor has to divide the greatest common factor, the highest common factor. And the second corollary, I'm going to finish here. I'm not going to prove this, but it's done in the notes. If P is a prime number, then, and P divides the product of two integers, M and N are two integers, I won't write that down, then P has to divide one or the other or both. When you say or, you always include the possibility that both statements are true. Now, you can prove that using the definitions that we've been talking about without discussing prime factorization. Of course, what this is really telling you, that given that P being prime means that it has no non-trivial factors. If it did, we could split the factors and have some dividing M and some dividing N, but we can't do that because P is prime. But we can prove this result using the notion of greatest common divisor. On the other hand, in the context of algebra, this can actually be used to define a prime element. So it's a very important property of prime numbers. In some sense, more important than the definition of a prime number. Okay, let me stop there. So please go over the very brief section 1, 2 in the notes, and then you'll be ready for the next section, in which we're going to use divisibility to revise the notion of residue or remainders or residue classes or congruence classes and modular arithmetic. Thank you.